Is Business Administration 2843 Business Statistics, and this is Chapter 8, Learning Objectives 4 and 5. The first one has to do with central limit theorem, which states if all samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution. This approximation improves with larger samples. Up here it says that the central limit theorem states that for large random samples, the shape of the sampling distribution of the sample mean is close to the normal probability distribution. Well, what does all that mean? It means if you have a larger sample size, large random samples, then you're going to get much closer to the actual values of the population. They try to illustrate this in the book by showing you, first of all, this picture on page 232. So first they show populations. Here's your population. This is the mean, the population. It's high on the left and the right. Here it's high over here, low over here. This is the opposite one over here. It's got a bit of a bend. This is uniform distribution here. So if our sampling size is 2, here's how they look. This doesn't look anything like that, and it's not a curve, bell curve. This one, over here you've got a peak here and a peak here, which kind of go along with this peak and this peak. Here you're skewing to the left. This one over here you're skewing to the right, just like the diagrams. And on the uniform, it's more of a triangular shape. If you increase the sample size, it looks more like a bell curve in each one. Not exact, but closer. And if we increase it even more, now it looks like a bell curve, each one, regardless of the population you've got up here. Notice these are all sampling distributions. This is X bar, the mean of each of these. Okay, so here's an example. And we've got how long somebody's worked for the company, how many people are there. It's skewed to the right. You can see that it goes way up here, starts up here, goes way high, and then tapers off. So if we get the mean of the population, we have 40 employees that have been here a particular length of time, and we add all those up and divide by 40, we get 4.8. So this mu here is the average of the population, 4.8. All right. Now we take a sample set of 5. We do 5 observations 25 times. And then for each one, we add up the numbers and divide by 5, because that's how many we've got in here. So 43 divided by 5 is 8.6. 35 divided by 5 is 7. Gives you an idea that the math is right. And we end up with these means all the way here. And we can take an average of these means and compare it to the average we get from the population. When we plot it, it looks more like a bell curve, but it still skews to the right. Once we increase the sample size, it looks much more like a bell curve. This is the graph of the years of service for 25 samples, but there's 20 employees in each sample as opposed to 5 up here. That's what we've changed. So in our table, it looks like observation 1, 2, 3, all the way up to 20 in each line. So then we add those 20 numbers and we get a total and divide by 20. So on this one, for example, on letter I, We add them all up and we get 80 divided by 20 gives us 4. So the process is the same. This length here, how many observations we have, just increases. And we add all these up and divide by 25, which is how many observations we had, we get 4.676. Notice the sub item on this mu. It says mu and it's bar x, which is the sample mean average. And 4.76 is not too far from the population mean of 4.80. And you get closer to it by taking a larger amount of observations. The next thing we want to look at is the standard error of the mean. That's this formula right here. So we've got a standard deviation of the sampling distribution of the sample mean. Okay, so let's look and see what it says here. If the standard deviation in the population, this one right here, the standard deviation of the sample mean is that standard deviation divided by the square root of n, where n is the number of observations in each sample. That's what's down here. That's the standard error of the mean. And that's going to be the standard deviation of the sample mean. All right. So I want to move on from here to 5 using the sampling distribution of the sample mean. So here's some examples they give first, and I want you to answer these questions. Here is a formula from 7-5, chapter 7, to find z, and z oh, wait a minute, I may want to do one of these questions here before I get into that. Let me go back. They were numbered different in the book and on the screen here. So number 2, it's number 12 in your book. We've got number of units sold last month by each representative listed below. These numbers right here. It says draw a graph showing the population distribution, compute the mean of the population, select 5 random samples, compare the mean, would you expect them to be about the same, blah, blah, blah. So we got to do a graph first, draw a graph. And I've got one here in Excel right here. Here's the numbers as they appear in the book. All I did was make a copy and sort them. I didn't have to sort them, but I did. And then I inserted a pivot table, which you do right here, insert pivot table. It says easily arrange and summarize complex data in a pivot table. So what I did is I created a pivot table and I counted the number of units. These are units right here, and I counted the number of units. So there were 5 2s, 9 3s, 3 4s, 2 5s, and a 7. It all adds up to 20. That's how many I have here. From row 2 to row 21 is 20. Right here I added them all up. I got 66, and 66 divided by 20 is 3.3. So this right here is the population mean, 3.3. And here's the graph of how it looks. So once I got this pivot table set up by doing this, then I just highlighted this and said, okay, give me a graph. Inserted a graph right here, and it showed me graphically what's being set up here. Frequency and units sold. Then it wants you to take a random sample, and you have to take your own random sample and add them up. You divide them by 5. The population mean is 3.3. In the example they gave, the sample mean was 3.32. It was almost exactly the same. We're going to look at another one of these without using Excel. We won't have a graph, but it'll explain it all. So let's go on then. To using the sampling distribution and sample mean. So here's some examples of where it might be used. We use this formula to find Z. And then it says here, finding the Z value of the sample mean when the population standard deviation is known. So we have to know the population standard deviation. Then you can use this formula to find Z. And it looks complicated. I rewrote it to look a little different. And I'll show you what that looks like. So they're doing all this mess here. And I think the best thing to do probably would be to show you an example. But I want you to keep in mind this graph right here, showing this curve. And you need to know what you're looking at. If you're looking at the part above here or below here. You can see that there's a lot more area here. All right. If you add up this number and this number, you get 0.5, because 0.5 is a half, and this is half over here to the right of the line. This is the other half to the left of the line. This is the population mean right here. That's the middle. So you're either looking, if you're looking over here, you're looking at part of this half, and the difference will be the rest of it. So you have a lot more area here. This is 0.4641. This is a lot of the area right here. This is like almost 93% of this side is right here, contained in all this space. Over here, you got 3.6 of the area in this part. So you have to know which one you're talking about when you do this. So I think rather than go through their example, and here's a number 3, which is not number 3 in your book, it's number 15. So I'd like you to go and try that one, but let me give you kind of a guide if I do what's number 16 in your book and number 4 on here. And I think I've got it here. I didn't open it. Let me open it. Gotta find it real quick. Oh, here it is. Okay, I've got number 16, which is this number 4 right here, in a document. So here it is, and I wrote out the question as well as the answer. So Problem 16, page 241. A normal population has a mean of $75 and a standard deviation of 5. You select random samples of 40, which you want at least 30. So 40 is a good number to get a good distribution of the mean. So now this normal population has a mean of 75. If we look back at that graph right here, then this would be 75 right here in the middle. Okay, that's what we know so far, and then the standard deviation is $5. So it says apply the central limit theorem to describe the sampling distribution of the sample mean with n equal 40. What condition is necessary to apply central limit theorem? Well, here we go. Here's the answer. The sampling distribution of the sample mean will be normally distributed with the mean equal to a population mean 75, and the standard error of 5 over the square root of 40, which is 0.79. Now, where in the world did that come from? Well, if we look back here, it's right there. The standard deviation, which was 5, divided by the square root of our sample size, which was 40. So it's 5 divided by 40 right here. 5 divided by the square, it's a word, Microsoft Word square root symbol. 5 divided by 40 is 0.79. So that's our standard error because of our sample size and our standard deviation. We said earlier, you have to know the standard deviation to be able to do this. All right, so what is the standard error of the sampling distribution of sample means? Standard error is 5 divided by the square root of 40, 0.79. Now we get into the fun stuff. What is the probability that the sample mean is less than 74? Now, whenever you get a question like this, you have to start in the middle. You have to start with the population mean. Population mean is 75. So what we're going to do, it gave us, what if it's less than 74? Okay, so we're going to have 74 minus 75, that difference, times the square root of 40. Why is that up here? Well, mathematically, you can convert, and let me pull it back up here. You can take, where'd the formula go? This formula, you can take this formula right here and take just this part, the square root of n, and put it up here. And that's perfectly all right. So the only thing you have underneath the line is the standard deviation. That's all you've got, just the 5 in our case. This formula works, it's perfectly okay mathematically, there's nothing wrong with doing it this way, and you have one less level to worry about. So you take the difference between this right here is your population mean. So you take the number they give you minus the population mean times the square root of n all over the standard deviation for the population. This is the population standard deviation. See, there's no subscript. So that's population standard deviation. So in our case, in this formula, we take 74 minus 75, which gives us -1, times the square root of 40, and then divide that answer by 5, and you get -1.27. Well, great. What do we do with that? Well, we look that up in a table, and that table is B3 in the back of your book, or another Z table. If you look online, you can find it. We want to look up 1.27, so let me show you how to do that. Here's the table. Here's 1 right here. Here's 1.2, and it was 1.27, so we'll just come across here till we get to 7, and there it is right there. 0.3980. So you've got 0.07, this is the second digit to the right of the decimal right here. And over here we've got 1.2, so it's 1.27. Where those intersect, that's our number, 3980. That's how we get that. So looking up 1.27 in the z-table, the value is 0.3980. Taking this from 0.5 gives you 0.1020. So there's a 10.20% chance probability that the sample mean is less than 74. All right, so the question said, what is the probability the sample mean is less than 74? If we look back here at our graph, this middle line is 75. As you go to the left here, remember it was negative 1.27, which takes us to the left. As you go to the left, the number gets smaller, and somewhere in here we have 74, maybe about right here. And it said, what is the probability the sample mean is less than 74? Well, from right here, 74, we go up to 75. We're asking about when it's less than 74, so it's to the left right here. So this is the area we're talking about. See, 74, if 74 is here, 75 is in the middle. We're not talking about between 74 to 75. We're not talking about greater than 74. We're talking about less than 74, which is going to be this area over here to the left. That is why when we look this up, we take 0.5 minus 0.3980. We're taking this part off 0.3980 and looking at what's left, 0.1020 over here. If you take 0.1020 and add 0.3980, you get 0.5. We're dealing with this half. And since it says less than 74, we're dealing with the part to the left over here. If 74 is right here, we're dealing with the amounts left of 74. Because if we go to the right, it goes to 75, and that's greater. This says, what's the probability the sample mean is less than 74? All right. Now it says, what is the probability that the sample mean is between 74 and 76? Well, we figured out that the area from 75 to 74 this way is 0.3980. Less than 74, it's 0.1020. So greater than 74 up to 75, it's 0.3980. And because it's the same distance on the other side, 74 to 75 is the same as 75 to 76, this part on the right is going to be 0.3980. So we add those two together and we get 0.7780. So there's a 77.8% probability that the sample mean is between $74 and $76. And that makes sense because most of your area is right here around the middle, 74 to 76. What's the probability the sample mean is between 76 and 77? So now we're looking at from 76, wherever it happens to be about here, up to 77. That's where we'll stop. All right? But when we do our calculation, we always have to go from, and let's look at that formula again, we have to go from the population mean right here, which is 75. So what I'm going to do is I'm going to go from 77 to 75. What's that look like on my graph? That's from somewhere in here, 77, all the way back to 75. That's more area than I'm talking about, but that's where I have to go because this second number has to be the mean of the population. So that gives me 2 times the square root of 40, all divided by 5. and it gives me this number, 2.53. Then I go back to the Z table, 2.5. Let's see if I can get rid of that. Okay. .5, and the first column is 0, 1, 2, 3, so 0.4943 is the value, the area for 2.53Z. So it's almost all of it, because all of it would be 0.5. And this is 0.4943. This is 2.5, and this is the 3 spot. So that's our number that we're dealing with, 0.4943. That's this number right here. Now we have to remove, now that's from this line and most of this, like up to here. But we have to take off the amount from 75 to 76. Well, what was that? Well, we did that earlier. 75 to 76 is 0.3980. So we take that off of 0.4943 and get 0.0963. Therefore, there's a 9.63% probability that the sample mean is between 76 and 77. We took off the amount from 75 to 76, and that made it way smaller. That'd be like, if this was it, if this was 76 to 75, it'd be all this. It's actually over here, it's even more. And then all we're talking about is the amount that's left, which is kind of small, and that's why it's under 10%. All right, then the last one, what is the probability of the sampling error? This is supposed to be X bar, I couldn't find that graphic to use it, minus mu, would be $1.50 or less. So what's X bar minus mu? Well, if we look back up here at our formula, here's X bar minus mu. Mu is 75. And it says, what's the probability the sampling error would be $1.50 or less? So we're going to take off $1.50 from the 75 and get 73.5 on the left. And we're going to add $1.50 to the other side and have 76.5. So there's a $1.50 distance from 75 for both of these numbers. So now we do two calculations. But we end up with the same Z because this right here is negative 0.9 when you do it, and this is positive 0.19, but there's still 1.9. And if we look at our Z for 1.90, we get 0.4713. So if we look that up, we get 0.4713, multiply that by 2 to account for each side, and we get 0.9426. That's twice this number here. Therefore, there's a 94.26% probability that the sample means are between 7350 and 7650. So I give you that as a form to go by to work on number 15, maybe 17 and 18, and then some at the end of the chapter. Try a couple of these, see if you can get them to work. If you can't get them to work, send me an email and I'll show you how it's done. If you have any questions, be sure and send me an email. Give me a call or something. Thank you.